Okay, so for example number 4, we have a 500 volt compound DC motor with a rated armature current of 1200 amps. And so that's a very large value of voltage for the power supply and a very large rated current for the armature. So we can believe probably that maybe that's a large motor, drives a very heavy piece of machinery, could be rolling paper in a paper mill, rolling sheet steel in a steel mill, or something like that. We're told that the total resistance of the armature circuit is 0.02 ohms, and when it's worded like that, it says the resistance of the armature circuit. So we're not given separate resistances for RA and RSE. We've been given that value as a single number. Okay, so now, I have taken the liberty of including the equivalent circuit. The source voltage, 500 volts. We're not given any information about the field circuit. The armature circuit resistance, and so you'll see here I've included terminals X and Y. I've included RSE. My little line here reminds us that RSE plus RA is the resistance of the armature circuit, and it is 0.02 ohms. We've included our armature, and we've indicated that the armature current is 1200 amps. Okay, so that's the information we've been given. Now, we've been asked to find the CEMF at rated load. Remember, that's E0. The total internal mechanical power developed by the motor, and want you to convert that to horsepower. And so remember that internal mechanical power, PMI. The armature circuit heat loss is the copper loss on the armature circuit. And that again includes, the series field and the armature windings. And the speed of rotation if this is the torque value. Okay, so we should start off then, part A. And if we're going to calculate E0, remember that E0 is going to be ES subtract the voltage drops in the armature circuit, and we just got one resistance value that represents the whole circuit. And so we can say then that E0 is equal to the source voltage subtract the voltage drops in the armature circuit, IA multiplied by the resistance there. And whether we put in the resistance just as an RA, which is the armature circuit, let's say, or we cause that RA plus RSE, we know that we just got that 1.02 ohms that represents that, right? Okay, so the applied voltage is 500 volts. And remember now that, when you calculate the voltage drop in the armature circuit, sometimes you might make the mistake of calling that E0. But remember, that's VA, right? And so E0 then, the voltage drop across the armature, the difference between E source and VA. And so, sorry if this looks like a negative sign here, that's supposed to be my decimal, right? And so we got our 500 volts, and this voltage drop in the armature circuit then, 1200 amps times 0.02 ohms comes out to be 24 volts. And so you see then that lots of current generally means very large diameter wire, and even though there's a lot of turns of that on the armature winding itself, still a very small value of resistance. And again, that's because 1200 amps got to go through there. That's typically very large wire. And so we come to the conclusion then that E0 is 24 volts less than the source voltage, and that gives us 400 and 76 volts. Now, part B, I think I'll move up here now for part B, and PMI is equal to E0 times A. And we got both of these values now. So 476 volts. And hopefully I can fit in my 1200 amps here. And so now that's a PMI, right? It's not PM. So then PMI, a very large value. And if you calculate that, we got 571,200, and the unit is watts. We're asked very specifically to convert that to horsepower, and so we can call that 571.2 kilowatts if we want to write it as kilowatts. And we're going to multiply that now by 1 horsepower over 746 watts. And if we want it to cancel with kilowatts, we'll use 0.7, that should be a 4, and so 746 watts per horsepower, right? And so 0.746, and the unit in there that should be in there is a kilowatt. And so now we'll say then that over here kilowatts cancels with kilowatts, and we're left with a unit of horsepower. So we've converted the horsepower if we do that calculation, and the number comes out to be 765.7 horsepower. Now that's PMI, right? And so that's not P out. P out we expect to be a bit less than that because there's a shaft loss. Generally they'll round then the power rating to a nice round number, and so I suspect what you find on the nameplate for that machine, 750 horsepower, right? That's a large machine, especially for electric motor. Now, part C asks for the armature circuit heat loss. Remember, the heat loss will be the I squared R losses when it comes to the armature circuit. And so what I was trying to put here was armature loss, and so that armature loss will be a copper loss, and it's I squared R. And so again, because we just got the one resistor value that represents all of it, it's an armature circuit loss, so it's IA squared, and because it's a compound motor, RA or plus RSE if we want to call it that. And so again, right, when we only got that one value, we may as well just call it RA, I suppose. But all right, RA plus RSE, and we got the 1200 squared is a big value, right? So 1200 amps, and let's see now if I can clean that up a little bit. And our 0.02 ohms. So still a bit messy with the stuff. However, we do that calculation and we come up with 28.8 kilowatts. Enough to heat a big home, right? So that's a lot of heat. Now remember, the motor got to be built in such a way that it got to be able to get rid of that heat. And so cooling, very important, right? Part of all that. Now, the last part for that question, we are asked to come up with the speed of rotation if the torque is 1600 Newton meters. And so remember now our equation for torque, and here I guess we'll say that it is torque developed, because we have PMI is equal to our equation for torque, right? 9.55 times PMI all over N. And so we have to, I'm going to move this down a little bit now. We have to solve that for N, right? So N is equal to 9.55 over PMI divided by T, and so equals 9.55, and remember our PMI needs to be given in watts here, and so 571.2 kilowatts divided by the torque that was given as 1600 Newton meters. Now, if that's a rated torque, really it should be paired with a rated speed and a power out. Here we got a rated torque, which we can assume is torque out. It's torque developed, because that's how the equation is defined. And so, you got to this is a bit of an approximation, but you got to work with the numbers you got. Generally, a power out should be associated with a rated torque. A PMI should be associated with a torque developed. And so here we got probably a torque out if it's a rated torque, but we don't have a P out because we haven't been given it. And so it's a bit of an approximation there, right? And so now we're going to say then that the speed, and that's, I guess, a rated speed, if we do the calculation, comes out to be 3409 RPMs, and so we round that to 3 significant digits, 3410 revolutions per minute. Now, any questions on any of that? Okay. Well, we're told very specifically now that the when we looked at the problem here, and right, we only got one resistance, and the phrase here, and I got my cursor lost. Okay. Yeah, we're told that it's the total resistance of the armature circuit, right? And so we can only assume that that means RA plus RSE, right? And so there's a comment in the notes when we talked about compound motors or talked about series motors that we said that that would sometimes be the case. So if that means RA plus RSE, when we goes down here to do a calculation, and we got RA plus RSE, then we just got the one value for that, right? And here, sometimes we'll be given those values separately, like in the previous example, which I think was example 3, we were given those values separately. And so you got to be a bit more careful there because you got two different values. Here we got the one that represents the armature, and it just depends how the information is given, right, and how the problem is stated.